Stream that. Okay, sure. Welcome to you. Welcome to our OpenPOWER Academia and Research webinar. Thanks for joining today's webinar, and my pleasure to have you all here. Today's session is on. The first one is going to be, presented by Dr. Shende from University of Oregon. Performance evaluation using Tao Performance System, and also E4S, Containerizing HPC and AI application. The second talk is going to be presented by my colleague Clarisse Hedglin from IBM, and she's going to be presenting about AI at scale in the enterprise. These two talks are going to be very interesting, for next 2 hours. And I would also like to thank Dr. T.V. Gopal, the professor from Department of Computer Science and Engineering, Anna University, Chennai, India, to support this webinar and also get a official approval from the Anna University to attend the webinar. Like many students and researchers are also attending this webinar as we speak. Thank you, Mr. T.V. Gopal, for this wonderful support. Do you like to say some words about the webinar, Professor Gopal?
Yes.
Please go ahead.
Good evening from India. It's my pleasure to welcome Professor Samir Shende and Dr. Clarisse on behalf of the head of the department. It is a very nice initiative that we have been working on under the leadership of our Vice Chancellor to see if we can have a very good collaborative environment to make sure that the students gain from the rapid advances in the field of computing and work with several international researchers, whether it is going to be in the form of some regular course in the curriculum or whether it is going to be a part of laboratory exercises. These are certain options which we are exploring internally. As far as the subject matter is concerned, we have begun work in the area of artificial intelligence and machine learning through our good colleagues in the department and professionals in IBM. Another course that we are working on with IBM, gaming and animation, 2 courses which we are trying to develop. We wish that both these courses will be explored not only in terms of the computing complexity, but also in terms of the societal reach and impact. One course, AI and ML, is very much in the computer science and engineering domain. Gaming and animation we are trying out through the media sciences. That we think is a good start for an exercise. It is true that we are also trying to have similar working groups through organizations. Have been with us for quite some time, 2-3 years. We will see how it progresses, how it proceeds. We also want a lot of our faculty members to get first-hand experience on these advances. Many things we will have to work it out internally, and by now our good colleague and friend Mr. Ganesh Narayan Swami would have apprised that Anna University is 500 students pass out of undergraduate every year. It's a wonderful institution. The College of Engineering Guindy, where I work, is celebrating its 225th year right now, 2020. It's a great institution to be with and a lot of positive initiatives. Plenty of flexibility is there. However, as all of us would appreciate in computing, scalability happens when there is a good interoperability. So we do have a sequel of procedures to follow to ensure that it will be a seamless interoperability across institutional frameworks that are independent by themselves, but they have to work together. They're completely independent. So, and then we have to also look at the kind of investments which my good friend here in Chennai, Parthipan, is collaborating with us for quite some time. several other regulatory frameworks that have to fall in place, but we have been experimenting with choice-based credit system, which gives maximum flexibility within these framework of operations. How best can we make sure that students across Tamil Nadu, wherever they are, whether they are in headquarters, capital Chennai, or in the southernmost tip of Tamil Nadu, Nagercoil, wherever they are, they will have advanced technology at their fingertips, good course materials, excellently trained faculty will be there on all these rapid advances. The Vice Chancellor is very serious, he is very dynamic. He says we will have to go through with that. Well, the world is going through difficult times. We began well at the beginning of 2020. Well, it's like that. 6-7 months has given me more study time to understand what are all these systems. All of us together will make sure that every student will gain from this kind of a rapid advance which technology is making. Over to you, both speakers, Dr. Samir Shende and Clarisse Hedglin. Thank you for joining. Thanks a lot. I look forward to the lectures.
Thank you, Dr. Gopal, for the motivating words. Thank you. And I welcome Dr. Samir to start the session now.
Thank you very much, Ganesan and Dr. Gopal, for inviting me today. I'm going to describe two tools, the Tao Performance System and the Extreme Scale Scientific Software Stack. Both of these tools are open source and they work well on IBM and other platforms. And the two challenges that I'm trying to address here is that with growing complexity, it's now getting harder and harder to accurately measure and optimize the applications that run on our large-scale HPC systems. These may be HPC or AI and ML workloads. And also, as our software gets more complex, it's getting harder to install the full software stack, to install our tools and numerical libraries in an integrated and correct manner. And to address these two issues, I'm presenting the Tao Performance System that aims to deliver a scalable, portable performance evaluation toolkit for HPC and AI ML workloads. And our website is at tao.uoregon.edu. And Tao is integrated in this extreme scale scientific software stack that aims to deliver a modular, interoperable, and deployable software stack where we can bring together many tools and libraries in an integrated manner. And it includes many products from the software technology area of the exascale computing project. Our aim is to also enable uniform APIs where there is a possibility. And the website is E4S.io. So to start with, the Tao Performance System supports many HPC platforms, compilers, and runtime systems. Our aim is to support all of them without any exceptions. And it provides portable instrumentation, measurement, and analysis capabilities. So there are three main components of Tao. The first one is instrumentation, or adding hooks to your program to perform the measurements. And these measurements can be in the form of profiles or traces. And once you generate the data, you can analyze the data using tools such as Paraprof and Perf Explorer that come from Tao, or third-party trace analysis tools such as Vampire from TU Dresden in Germany. So we support automatic instrumentation of many different of programs written in many different languages, including Python, C++, C, Fortran, and Chapel, among others. We also have support for instrumentation at the runtime level. So if you're using the message passing interface, or MPI, or OpenSHMEM, or pthreads, or OpenMP, we can instrument the programs without any modifications. We also have support for GPU, such as runtime systems such as ROCm for AMD GPUs, CUDA, OpenCL, OpenACC, and all of these runtime systems allow you to express parallelism inherent in your application. We support both profiling as well as tracing and analysis tools. So you're probably wondering, how can Tao help me? What can it show me? How can it guide the performance engineering of my applications? Well, Tao can show you how much time is spent in your application code regions. These could be routines, outer loops, inner loops, and within loops, it can show you the contribution of individual statements. You can see the time spent in your OpenMP loops. You can see the time spent in GPU kernels, and it can show you the data transfer between the host and the device. Instead of time, if you prefer to see low-level processor-specific instructions, such as the total instructions, floating point instructions, data cache misses from level 1 and level 2 data caches, branches taken. We also have support for packages such as PAPI and Liquid. You can measure the memory usage of your application. You can see where it was allocated, deallocated. You can see the memory footprint. And I mean the total memory, including the stack, the heap, the data, text, BSS, the full memory usage of every process and the total across different ranks, and the maximum memory that your application used during its lifetime at the end of the program. You can also measure the energy or the IO or how the application scales. Now, to do this, you need to add hooks to your code to perform the measurements. And that is the process of instrumentation. Now, you can add hooks using a preprocessor where you can start and stop individual functions or loops. And that is done through pre-processing of your source code using compiler scripts that Tao provides, such as taocc.sh, taof90.sh. We can also use a filter file to reduce the runtime overhead. You can also use the compiler to insert these hooks directly at the routine level. But the most interesting part is that you can use preloading of the Tao dynamic shared object or shared libraries using a tool called Tao exec. So if you launch your application, say an MPI application using MPI run app, then you can just insert the Tao exec command between that and say MPI run Tao exec app, and it will generate the performance data for you. And it will generate profiles as well as traces. Now, profiles can show you how much time was spent in your application regions. So your code regions, such as functions and loops, can be highlighted, and you see the total summary, the summary statistics across the execution. So if there is a function, say a solver, that gets called 100,000 times, then you will see the total contribution of that solver across the 100,000 invocations. Now, tracing, on the other hand, can show you when the events take place along a timeline. And here you can see along the timeline what each rank of your application was doing. In this case, you can see message sends, you can see the functions that are invoked by your individual processes. Tracing generates a lot more data. With Tao exec, you can use the runtime preloading capabilities of Tao and insert hooks in the runtime layer. So if your runtime is CUDA, OpenACC, or MPI, you can insert the hooks at that level and then enable other options in Tao, such as event-based sampling, or generate a communication matrix display, or generate the open trace format OTF2 traces that can be visualized in a tool such as Vampire. So the important thing to remember here is that there is no modification to your binary. Unmodified executables can be launched simply by Tao exec to generate the data. And this is how it typically works. If you have on any major HPC system, you can see the system administrator may have already created a module for Tao. All it does is puts Tao in your path so that the tool Tao exec is accessible. If you're running an uninstrumented program with MPI, then you can just simply say MPI run -np64 Tao exec with the EBS flag, or event-based sampling, and use it out. If you're using OpenMP programs, then say with the Clang compiler, then you can enable environment variables. And there are many environment variables. I'll touch on them. You can say Tao exec -t or tags, which identify a unique configuration. So you could say tags for MPI with pthreads, or OpenMP tools interface version 5, and enable the OMPT and launch the executable. So just adding this line can then show you all the time spent in OpenMP calls. You can observe where the loops begin and end. You can see the forks and joins. You can see the complete profile at the runtime level, and then also enable event-based sampling as an option. And you can use these together. So then you can see what's happening in the rest of your code. If you have a Python code, as many of our users are using with frameworks such as Horowad or using TensorFlow, you can say Tao Python instead of Tao exec, and then you will also see what's happening inside the Python layer. And if you have a GPU code, then you can use the CUDA profiling tools interface or CUPT, and then even enable event-based sampling and use the Tao Python to see the performance of your MPI, CUDA, and Python application. And once you generate the data, you can just launch pprof or paraprof. Paraprof is our GUI. If you want to generate traces, you must enable the Tau trace option and then specify a format to generate Vampire traces, which don't require any merge or convert operations. You can just launch your application and then launch Vampire, or you can use the Chrome browser with the Chrome tracing, but there you have an additional step of tracing and then merging and converting the traces. And that's also the case with JumpShot. JumpShot is a tool that comes from Argonne National Labs, and it's shipped with Tau. And you can launch the Paraprof browser. Here you can see all the MPI ranks. These are all the threads. And you can see the time spent in individual functions. Let me just take a moment to show this to you over. Here is execution of Paraprof. This is a profile browser, and now you can see the time spent in every node. So you can see this loop took 279 seconds of exclusive time. And you can scroll through this. You can unstack the bars so you can see what is the times taken in MPI barrier across multiple ranks, or you can use the 3D visualizer in Tau. And this shows you all the MPI ranks over here and all the functions over here. And then you can see the shape of your application. This is a triangle plot. This is a bar plot. And you can see what each function is doing. So you can see the shape of this function is inverse of that. You can look at specific loops across different ranks and zoom into a portion. So here with the first mouse button, you can rotate. The second mouse button, you can translate, and scroll wheel, you can zoom in and out and see that there's this loop over here. And at thread 199, it took 129 seconds. So it allows you to see the shape. You can see the two halves of the machine. You can also see topology plots of what any one function is doing. In this case, you can see the color and that particular loop across the full system. You can look at the scatter plot, which shows you 4 different functions and their minima to maxima values, and see that there is one thread that's different from the rest. So you can dive deep into your code and then see exactly what each rank was doing in your application. So this is a very powerful visualizer. It's all written in Java with OpenGL, and it works across multiple systems. So with this background, let me just jump right back into my slides. I may not have time to cover all the slides, but you can try these tools. You can see the time spent in individual kernels written in your code. You can use Tau Python instead of Python to launch your application and specify a given configuration of Tao. You can even see Python codes with sampling and see what each of them are doing. Look at the inclusive and exclusive time spent in your application. Go down to the source level, see context event windows that show you the data transfer or the host to device transfers along a particular calling sequence. You can even go down inside vendor libraries. And that's right. This is an application that was run on the IBM Power 9 system. I believe it was on Summit at Oak Ridge. And then you can see inside the MPI Bcast exactly what the IBM library was doing. And you can see the calls made by the PAMI interface. And I thank the vendors for not stripping their libraries before shipping them. And so just with a simple Tao exec or Tao Python tool, you can then see exactly what each of those libraries were doing and where your application was stuck. In this case, it was taking about 12.21 seconds. Now, this is interesting. It says that with start and stop timers, the time spent exclusively in MPI is 12.26. But with sampling, where we take a sample by periodically interrupting the process, we can explain not 12.26, but just 12.21. And so this is close enough. And you can see this is the addition of all the samples in the MPI Bcast in a context node within MPI Bcast. And it says that this PAMI context lock took 3.27 seconds. And the pthread spin lock took 2.34 seconds. And you add these up, you get to 12.21 out of 12.26. And you can observe what was going on in vendor libraries. You can even unwind the call stacks using this Tao EBS unwind and see what's going on inside AI frameworks like TensorFlow and observe samples that are collected in individual per thread executions. Here is an example of a C++ or Fortran application where you can just launch it with event-based sampling, or call site instrumentation, where you can partition the time spent in a function across different call sites. So it says that instead of seeing the total time in MPI receive as 14.6 seconds, MPI receive called from this exchange1 function at this line 68 in exchange1.f took about 12.6 seconds. You can see the bandwidth, the write and read operations, the 3D profile browser, communication statistics, or even traces. You can also observe this in the Chrome browser that many of us use on our laptops, and you can launch it with Chrome tracing, and it will show you a flame graph, which shows the levels of nesting from your applications. We also have support for Cocos, and Cocos is an emerging runtime that allows you to express parallelism, and this is shown with the Vampire trace visualizer. And you can have a mix and match of different runtimes too. We also support MPI, pthread, OpenMP, OpenACC, OpenCL, CUDA, ROCm, Cocos, Python, and a combination of these. So you could mix and match and say, I have an application that uses Python with CUDA, with MPI, using say Horoward, and then I want to use all of these features together, and then you can pick the Tao exec and launch it with this parameter, which says either kubectl or OpenCL or OpenACC or OpenMP tools interface, or enable event-based sampling for the rest of your application. You can also specify if I want to observe the data at the level of functions or files or line resolution. We also have support for automatically inserting hooks into your code using PDT that has parsers for C, C++, and Fortran. And you take the original source code, you analyze it, you insert hooks in it, and then you can also specify a selective instrumentation file that says, please instrument this or don't instrument these functions. You install PDT first and then point Tao to this while you install it, along with other packages such as BFD, which is very important for translating the address into the source line location number. and unwind for unwinding the call stack if you choose to do that. And then you can select a configuration of Tao, which is specified in the architecture lib directory as makefile with these tags, the same tags that you use with Tao exec. And then you can substitute the compiler. So instead of MPI-CC, you can say, please use taocc.sh. And you can install Tao on your laptops. And when you instrument your code, you can load the module to get Tao in your path and choose a specific configuration of Tao where you can have multiple configurations. You could configure Tao with, say, IBM or Clang or PGI compilers with support for PAPI or CUDA. And then each measurement configuration then has a unique stub makefile. And you can then substitute the compiler. Instead of MPI F90, you can change it to taof90.sh, compile it, create an executable, run it, and then launch paraprof. Now, recall that instead of using source instrumentation, you can also use compiler-based instrumentation. Here is an example of how Tao is installed on an HPC system at Oak Ridge. And you can see that these are the configurations for Excel compilers where they have used a specific tag. And then this is how it looks like for the GCC compiler. This is Tao version 229.1 on IBM 64 Linux platform. And then these same tags are then used to identify that configuration, because when you configure Tao, it builds this makefile and then puts the libtao.so in a shared directory. And then you can use the same comma separated list of tags. If you want to use a non-MPI program, you must use the -t serial as an option. You can specify compile time options using the Tao option. So you could say, please use the compiler-based instrumentation and not the source instrumentation to generate the executable, or specify the location of a selective instrumentation file. And then you could then specify what should be instrumented, such as loops in all the routines. Hash is a special character like the clean star, and it will match one or more characters. So in this case, you could specify an exclude list and say LHS 32 in it, and a hash will match the 32. You can also create a selective instrumentation file directly from paraprof, or you can specify a selective instrumentation file at runtime instead of compile time. The idea is you can filter the routines and zoom in to just what you want to instrument. So you could say, I just want to instrument main and these 5 functions and nothing else. And then you can focus your efforts of instrumentation on a specific code region. You can also exclude instrumentation in frequently called routines that are trivial because they take very little time. And you can create a selective instrumentation file directly, because when you run the program with Tao, it throttles those functions which take, say, less than 10 microseconds per call of inclusive time and get called over 100,000 times, saying that, oh, these functions are trivial. You should not access the system clock. And then create the selective instrumentation file and then load it either at runtime or at compile time. Here are some of the Tao environment variables that you can set, and then reduce the instrumentation cost in your code, get most accurate results, and analyze where the application is spending time in its execution. So Tao is a very versatile tool. It is available as part of the extreme scale scientific software stack, or E4S. And E4S is a community effort. It's a community effort to provide open source software packages for developing, deploying, and running scientific applications on HPC platforms. And we support both from source builds as well as containers of a broad collection of HPC software packages. Now, you may have used virtualization approaches such as VirtualBox to deploy a whole operating system and its components on a given platform. Well, containers are more efficient than VirtualBox-based approaches. They have this only one kernel executes. So your host operating system kernel allows you to execute containers, and these containers can consist of a whole operating system stack with packages. You can deploy it using HPC container runtimes, including Docker or Singularity, and they run on IBM, x86-64, and other platforms. So E4S exists to accelerate the development and deployment and use of HPC software, to lower the bars, to lower the barriers of entry for HPC and AI ML community. It includes many packages such as MPI, tools like Tao, PAPI, HPC Toolkit. It includes math libraries such as PETC, Trilinos. It has data and viz tools, and it has a full set of AI and machine learning packages, including TensorFlow and PyTorch. There are many software development kits, SDKs for math libraries, data and visualization, programming models, and runtime. I lead the SDK effort for programming models and runtime for the exascale computing project at the University of Oregon. And we are creating this E4S release where we integrate, build, test, and deploy the packages. So it's a curated release of ST products. And we also provide binary build caches so that you can have bare metal installs. So if you have a new system, you can use the SPAC package manager. You can download SPAC from spac.io, and then you can just point to our build cache, and then you can install these packages very easily directly on your bare metal hardware, or you can use containerized distributions that we provide with base containers. You can create custom containers or use a full featured container, which has support for GPUs. We also provide a virtual box image with many of these container runtimes, and these can be very useful for teaching the concepts of virtualization, the concepts of using containers, including Docker, Singularity, Shifter, and Charlie Cloud. Charlie Cloud is a container runtime that comes from Los Alamos National Labs. We also have support for deploying this E4S on AWS. And it's released twice a year. We have a set of packages, and you can download it from the E4S download page. Here is an example of the PPC64LE image of Docker, or you can get it directly from Docker Hub. If you have Docker installed, you can just say Docker pull and ECP E4S and then give a name such as this, and it will download it. And it includes CUDA. So if you have a new system and you're just installing, say, Docker or Singularity, you can be productive with this full stack of software packages, including Tao, by just using this one command. Here is the list of 46 different ECP products under the Ubuntu 18.04 distribution with support for NVIDIA GPUs. And you can access the GPUs directly from Python. Here is an import for Matplotlib, for TensorFlow, for PyTorch. And I can say TensorFlow is GPU available, and it shows me that. Or you can use Singularity from Scilabs. You can just download it from scilabs.io. And once you have Singularity installed, you can download our PPC64LE image. And this is just one file. If you download this one file and say Singularity exec with the --NV flag, this is for NVIDIA GPUs, then you get a fully operational shell where all of these packages are pre-installed. And here is an example of using Singularity and accessing the GPU. And it's all based on SPAC, the SPAC package manager, which is used as the primary vehicle for software delivery. It's a very mature package manager, and it's gaining in popularity across the world. The reason for that is that scientific software is becoming extremely complex. Here is an example of NALU, which is a generalized unstructured parallel low mark flow application. And you can see the number of packages in the dependency where NALU depends on, say, Trilinose, which depends on sweet sparse, which depends on Metis, and all of these packages. Here is a dependency graph for deal2. Here is one for RMiner, and it's getting more and more complex. Even proprietary codes are often using a lot of open source packages. And to use SPAC, you can just clone this repo and source it and then install the packages such as SPAC install Tao, and it will do all that. You can just say install Tao or Tao at 2.29.1, a custom version, or say that use GCC at 730. So what this shows is that SPAC understands versions. It understands compilers specified with a percentage symbol. And you can specify custom compilers. You can even specify variants of a given recipe or a spec where you can say, I want to use support for MPI and Python and pthreads, or say that I want to use MPI, but please use the MVAPICH2 distribution, which is very optimized for InfiniBand interconnects, and then say, don't use the wrapper RPath option, use the version 2.3 of MVAPICH2 while configuring Tau. And if it's not available, it will install everything for you. And then you can just say SPAC load Tau. Here is an example of Docker using our image, and you can just say SPAC find and see all the packages that are installed in that image. You can visit the spac.io webpage, and our colleagues from Lawrence Livermore National Labs are developing this tool, and the SPAC community is growing rapidly. It uses E4S even for its pull request testing, and we have support for a full E4S container-based build whenever a pull request is merged. And we have build cache and container build pipelines. You can see more information about all the products that we have in a build cache, which has binaries. So you can just download the binary for SPAC directly from our website. And here is an example of just PPC64LE. And you can see we have over 6,000 SPAC packages, binaries, built for different OSs for many different packages. And you can search it, you can pick from OSs such as CentOS or Red Hat Enterprise Linux or Ubuntu, including Ubuntu 20. All you need to do is get SPAC, download our key, trust it, and say SPAC mirror add E4S, and then point to this cache.e4s.io website. Here is an example of using E4S build cache for speeding up the install of your application using our build cache. And here is an example of the SPAC cache web page that's under development. We also have a doc portal that rakes the different repositories and puts in all the information in a web page, which is a single online location for accurate product information. So you can click on, say, Petsy, and it will show you the latest information from their README files, the license file, and so on. And here are images. Now, what is interesting is that we have TensorFlow images posted to the Docker Hub. So if you wanted the latest version of TensorFlow, say TensorFlow 2.2 with CUDA 10.2 for PPC64LE IBM platforms, you can get these images directly from the Docker Hub page by just doing a pull, saying a Docker pull on that particular TensorFlow image. Here are different OSs, including Ubuntu, UBI. UBI means Red Hat Enterprise Linux based base image, and CentOS. What UBI allows you to do is, if you have a Red Hat license and you are using a UBI image, then your container is supported by Red Hat. And all the packages running there come under the Red Hat support license. So it's a very interesting way to have a fully supported software stack from IBM and Red Hat, where the UBI containers have all our ECP packages, including Tau, and then you can have a supported image from RHEL. We also have support for Ubuntu and CentOS images, and reproducible Docker recipes that you can use for base images, all available from these web pages. We also have a build pipeline for multiple architectures and OSs that we are using to build with GitLab at University of Oregon, and a validation test suite. Now it's important to validate the packages that you have built to make sure that they can be compiled correctly, they build, run, and here are base images that are used. We are also supporting VirtualBox with different container runtimes, such as Docker, Shifter, Singularity, Charlie Cloud, and a tool that we are developing internally to simplify the launch of MPI jobs that are used with E4S containers. And E4S containers include support for replacing the MPI libraries, the message passing interface libraries, using the ABI compatibility layer of MPICH. So you can build an application on one platform and run it on another using the same container of the same ISA, of course, but you can replace the MPI while doing that and improve the launch. And it is a tool that we hope to demonstrate soon. We are also working with visualization tools and GPUs for supporting these with E4S. We are working closely with the DOE LLVM effort to bring together many different features of LLVM and the research capabilities being developed by the Department of Energy in the US. We have support for continuous integration, deployment at facilities, scalable startup using super containers, and improving the launch of MPI applications. So to conclude, I would say that Tao provides a versatile tool to measure the performance of HPC as well as AI ML workloads. It's part of a bigger ECP E4S project. It provides a well-integrated software stack for AI or ML and HPC for IBM PPC64 LE and other platforms. It provides from source builds as well as containers, full featured containers for deployment, and Docker and Singularity images are available for download from our e4s.io webpage. You can download Tao from the Tao webpage as well, and it's all BSD style licensed, open source, free. This is the Performance Research Lab at the University of Oregon in Eugene, our beautiful campus. Of course, the campus doesn't look like this right now. It's bare, but we hope things will improve. We would like to thank various organizations for their support of the Tao and E4S project, including the US Department of Energy, Argonne National Labs, the Office of Science, Exascale Computing Project, SIDAC, Lawrence Berkeley National Labs, Lawrence Livermore National Labs, Los Alamos National Labs, and Sandia, PNNL and Oak Ridge National Labs, the Department of Defense, National Science Foundation, NASA, the CEA in France, and our partners at the University of Oregon, the Ohio State University, the developers of MVAPICH2, Paratools Inc., the University of Tennessee, Knoxville, the developers of PAPI, TU Dresden in Germany, the developers of Vampire, Jülich Supercomputing Center, the developers of tools such as Scorpy, and Opari. I thank the Exascale Computing Project. And before I show you a demo, I'll take on any questions. Are there any questions that?
Yeah, thank you, Samir. There are some questions from Dr. Gopal on the chat window.
Okay, let me. I'm trying to get this chat window to mute show chat. Yes, what applications have a linear relationship of number of cores and performance? If you are referring to like embarrassingly parallel benchmarks, then there are applications like the MBAR. There are several applications that have such a linear relationship, but there are limits. There are always limits, and you will see the scaling curve taper off at a certain number of cores, because as the number of cores increases, the overheads and the serial parts of the code continue to dominate. And you have limits to that scalability, but there are some examples that you can see for that. Any result on the impact of atomic operations on the parallel performance? Yes. So with using tools such as Tao, you can measure the time spent in individual runtime system operations, such as atomic operations, and different synchronization operations. And there is an impact on the scalability of the codes, of course. Just to confirm, is this software stack complete ecosystem? And the answer is it's an attempt to create an ecosystem of tools. Yes. And here is an example of using it, say, on a system. Let me show you. This is an IBM system with 4 V100 GPUs. I can see there are some processes running on it already. And I can launch the software by just going to E4S.io, going to the download page, getting this Singularity image from here, and then just downloading that image. Once I get that one file, I can say Singularity exec with the --NV flag, and I'll just run this command and say bin bash with the RC file. So I have just downloaded one file from here on an IBM system, and now I have SPAC in my path. So I can say SPAC find, and it shows me all the packages, the Python packages, the solvers such as sundials, SuperLU, Trilinos. I can say SPAC location to see where, say, Trilinos is installed. And here is the location. Trilinos provides linear equation solvers, and I can then see inside this, and all of these libraries, libml, that are coming from this package. It's the same way SPAC find PETC, and it will show you which version of PETC. You can say SPAC find -dl-v PETC, and then it will show you the dependency tree, and here is a hash for PETC, and you can see exactly how it was configured, which packages it used, like HDF5, OpenBlast, NumaCTL. These are all pre-installed, and so are the Python tools. So I can access the GPUs. Here is NVIDIA SMI running from within Singularity, and I can see the GPUs. I can say Python, say import TensorFlow. And now I will be loading the TensorFlow. So if you were to try and install these packages yourself, it would take a lot of effort to install, say, PyTorch or TensorFlow, install it in a way that accesses the GPU. And if you want to see if this one is able to access the GPU, you can see TensorFlow adding visible GPU devices. And there are 4 devices, V100 SXM2 with 32 GB. This is showing that it's able to communicate over NVLink, this GPU. And that's a unique architectural characteristics of this AC922 system, where the CPU, the Power 9 CPU, is connected to the GPU, not by the PCIe Express bus, which is very slow, but with a 150 Gbps NVLink 2, metal link connecting the CPU directly to the GPU. So the data transfer between the host and the device can be very significant. And here are 4 GPUs in one IBM box. So I can access that if I want to see how much time is spent in different operations. Here is an example. Here, if I say clean.sh cat compile.sh, so I'm just saying spac load CUDA, okay? And now I don't have to install that. It's, in fact, in this case, it's already installed here. And I can say nvcc, which is in my path, and I can say matmult, and it will run the code on 4 NVIDIA GPUs. Now, if I want to profile this application using Tao, Tao is already inside in my path. And I can just say Tao exec -t kupti matmult. And I can say use not the MPI configuration, but the serial configuration with the -kupti flag. And once I just launch it with Tao exec, I did not need to modify the binary in any way. I just launch it with Tao exec, and it will show me the time spent in each of those kernels that execute on the GPU. So you can see the time spent in CUDA application routines, CUDA runtime routines like CUDA stream synchronize. You can see the time spent and the bytes copied from the device to the host. And you can see on a separate thread, a GPU thread, that events that occur over here. So thread 3 is showing me multiply matrices, the kernel that ran for 1.3 seconds on the GPU. And this is thread 4 and thread 6, which shows again the multiply GPU. So you can see on a event on a thread by thread basis, the time spent in all the GPU operations without changing anything in your application. Here is an example of molecular dynamics application, SRC MPI. And here's an MPI application. I can say make, and I'll be able to build it. If I go and launch it, I can launch it by saying something like this. Launch it on 4 ranks like this. Or if I want a bigger problem and I want to run it with just Tao exec, I can take this binary and say Tao exec with event-based sampling. And then I'm specifying a much bigger test case over here. And this molecular dynamics code is running now on 4 CPUs on the IBM Power 9 system. And I should be able to generate detailed profile data without modifying the application binary in any way. And I can even show you how I might create the data files on one system and then transfer it to another and generate the data. So here are profile files, and I showed you pprof. I can say paraprof --pack and give it a name like this, and then say transfer it over and bring it back to my laptop and say so if I'm wondering where did this application spend its time, I can look at the thread statistics table and say the application took about 30.2 seconds. And out of these 30.2 seconds, about 0.18 seconds were spent in MPI all reduce. MPI send receive call took 1.2 seconds, and about 28.8 seconds were spent in the rest of the application. Now, with sampling, we cannot explain 28.85. We can explain 28.62. So see, this is the difference between precise timers and what sampling can provide. But this is close enough. If I can explain what happened in the rest of the code with the precision of 28.62 out of the 28.85 seconds, I can open this and then see all the functions. I can even sort it by that. And here it says that there are functions like sort atoms in cell, advance velocity, get box from coordinates, but there is this one function called LJ force, and it's taking 27.3 seconds out of the 28.6 seconds. If I expand that, I can see the time spent in this line number 199 was 5.91 seconds. In line 202, it was 3.96. I can even see the source code, which I have in fact downloaded previously. And this is the line. Now here, if you see in this LJ force function, in this molecular dynamics application, there is a for loop here, 1, 2, 3, 4, 5. 5 levels of for loops, and it goes down to that line. And what Tao is able to show you is that in this line number 199, it is taking 5.9 seconds. This is the function that you should focus your attention on. It's taking as much as 27 seconds out of the 30 seconds. And this is the level of nesting. This is the loop that's taking up a lot of time. And you should focus your attention in this inner loop from this function called LJ force. You can see the full profile. You can see the 3D view of how the application looks like. Bar plot each function by function. And this is the LJ force summary, this big wall that you see. And you can see the threads, 27 seconds, 28 seconds, 27 seconds. You can zoom in and see what every function was doing in your application code. And here are the lines of the samples where the application is spending its time. This is line 199. So you can observe this, the full shape of the application. So thank you. Are there any other questions?
Samir, there are questions in the chat window as well as the Q&A table. But in interest of timing, let's move on to the next session. Anyway, thank you for your wonderful presentation and also the demo. This will be really useful for the students, in Anna University as well as the across, other people who have joined this webinar. And with this, I just want to announce also for the students, and if you guys want to have a infrastructure like Power9 system, put together a proposal, what kind of project you want to work on, and send it to us, and we can evaluate, and we can even give you access to systems like what the Samir has run, some of his the performance tools and the E4S kind of the software. So this is a great opportunity for you to collaborate with the University of Oregon and the IBM platform and also the OpenPOWER Foundation. Samir, again, thanks for your wonderful presentation, and thank you. And let's participants, let's move on to the next presentation. My colleague Clarisse Hedglin, who is going to be sharing our experiences in AI scale in enterprise. Clarisse, please go ahead and start your presentation.
Thanks, Ganesh. Can everyone hear me?
Yes, that's good.
All right, so the topic I'm covering today is AI at scale. I've covered this topic in the past on how it applies to HPC, and how you get scale by leveraging multiple GPUs within a server and across servers. But this presentation is mostly focusing on how it applies in the enterprise and what machine learning and deep learning mean to data analytics and how it's leveraged in client situations. So a little different from some of the traditional HPC type topics. So we're going to talk about how people are doing data analytics today. Then we'll cover what we mean by the AI ladder and talk about an AI lifecycle. We'll touch on some of the common themes in AI in the enterprise. We'll talk about some infrastructure considerations and conclude with a couple examples. So how do customers do data analytics today or traditionally if they haven't started their AI journey? A lot of the data that they analyze to get insights comes out of spreadsheets. There's no governance, there's no collaboration, and it's fairly simple. There's also business rules that are applied. So these are high-level rules of data analysis based on the data. If the data is doing a certain thing, then you take a certain action. Not very dynamic. There's also a lot of homegrown applications that are based on some of these business rules that are preset rules and approaches. And the challenge there is that it's not very flexible, and the rules to change those rules dynamically are quite difficult. But it's usually very tailored to what the insights you need from your data, and that can apply across all industries. And then finally, there's other packages and applications, independent software vendors that prepare and package your data to give you insights. And that involves some hard-coded models that do specific things. And some of those challenges are maintaining those packages and keeping up with the information that you need. And again, there's some challenges with getting real-time responses. So the idea is, how do you modernize? How do you modernize the data analytics? And of course, people jump right to the answer of applying AI, applying artificial intelligence, applying all these new techniques. But the point I want to make here is that it's a journey to get there. So you'll start with your descriptive analytics, which is some of what we just talked about in terms of looking at spreadsheets. What has happened? So you have the data and you want to take an action, and most of the work between the data and the action is driven by human intervention, manual analysis, moving data on your own, and basically just understanding what has happened in the past. Then you can move on to a more predictive type of data analytics, and that's predicting what will happen. And so that's been going on for many years already, but there's still a lot of human interaction that goes into defining specific rules and looking at your data more statically. Finally, you can get into prescriptive and cognitive phases, and that's where you're really getting to the definition of the action that you want to take based on your data. So with prescriptive is what should we do, and that's where you can start building models that look out into the future, that look at your data historically, that look at features in your data and start applying machine learning. Finally, you can get to the cognitive piece where you've got more and more automation and more insights from historical data and from data from various sources, where in fact the data piece is the biggest and most important factor in your analytics work. And the human interaction is coming from final checks and defining how to look at the data and basically letting the data help you define what your actions should be based on the insights that you're getting from the data. So some common patterns that we see that start to apply AI include use of deep learning, and that's when you're able to look at text images, videos, and insights, and looking at supervised, unsupervised methods of your data. So this is where you start applying machine learning and deep learning. And the advantage here is that you're now letting the data dictate the insights, and you're using mathematical formulas under the covers and having the systems, your AI systems, learn from the data and from the formulas that you apply. So when we talk about AI and the types of use cases that apply to getting insights from your data, we generally think of it as multiple categories of use cases. So you've got some more traditional data use cases, and that involves structured data. This is, in fact, data in spreadsheets, big data, where you've got features defined, rows and columns, and you can get a lot of insight from that structured data. We also are seeing a move into unstructured data, and one of the biggest use cases there is relative to computer vision. So this is more where you can apply machine learning, but you can also apply deep learning, and this is really exploded recently in the last 10 years because of access to GPUs, so more compute power, better algorithms that are coming out of the open source and universities, and an explosion in unstructured data. So this is data that is images, free-form text, so on. And what you can do with this is apply these deep learning algorithms and get insights on vision, where you can actually do classification of images, object detection, action recognition, segmentation. And when I talk about vision, you typically think of an image with pixels, but anything that can be translated into an image with pixels, such as audio, sounds, or satellite data, or LiDAR data, there's a lot of alternatives to apply these deep learning methods that basically come back to these vision algorithms. And then finally, the last case of use cases comes out of natural language processing. And this is all the science that uses machine learning and deep learning under the covers, but that drives understanding of language, whether it's text analysis, documents, looking at research documents to come out with context, looking at intents in chatbots, looking at translation of languages, real time. So this is a very specialized area of use cases, but that we're already seeing pervasive applications across the industry and research. So as I mentioned, all of these techniques are being applied. We are seeing this across all industries. Fraud is a very popular use case, whether it's banking or insurance or medical reporting. Safety inspection, process improvement, quality inspection, making sure that we've done some use cases recently on detecting social distancing and mask wearing, those kinds of examples. And then finally, many use cases in defense and security relative to applying AI. Now there's a Forrester research report that's already actually a couple years old that that determined that AI is the fastest growing workload. And we're seeing that across all industries. And as I mentioned, through different types of use cases. So what we've been working on specifically is this journey to AI and what the steps are to get there. One of the ways to organize this is what we've been calling the AI ladder. And in fact, there's been some books recently and documentation published that goes into great depth in terms of what this means. But at a high level, again, you're taking data, you're looking for insights, and you want to apply those insights to your solutions for your problems, whether they're business or research problems. And the steps are collecting the data, so making data simple and accessible, organizing it, creating a trusted analytics foundation so that the data that you need to get the insights is readily prepared so that you can go to the next step, which is analyze. And that's what we're talking about here in terms of scaling the analysis. So this is mostly about model training and development and making sure that you're set up to get to the final step, which is infusing your AI into your applications, into your business processes, and operationalizing it across your whole organization. So a lot of this is tied to modernization of taking the way you do things today and moving them into this newer view of things and applying AI to get faster, better results and insights from your data. So clearly, to get to that infused piece or deployment, if you will, you need to start with the data. And we talked a little bit already about structured versus unstructured data. The idea here is that it's much more than those two categories. Your data is going to come from many, many different sources and be of many different formats and types. And so your storage architecture and flow is going to make a big difference in how you build up your AI savviness. So some of the examples are using enterprise data, such as transactional and application data. This kind of data could be running on mainframes, it could be running on Unix servers, on x86. It's really more tied to what the application and the workload is. And the idea here is to keep your AI as close as possible to your data. So transactional and application data is one of the big sources of data. And the quicker you can get the AI to that set of data, the more effective you can be. Then you've got machine data, instrumentation, sensor data. This is all the data that's potentially out on the edge that is giving you feedback from your devices, from different sensors, whether it's temperature, speed of reaction of manufacturing lines, so on. Enterprise content we talked a little bit about already, but that can be also warehousing content and other insights that you're getting from your enterprise. Images, geospatial, and video data is the new and emerging hot area of AI, as is social data and other third-party data. Big example there might be weather data. And you can see from the types of data that you have, whether it's real-time data that's coming through your databases or your streaming information, whether it's operational data or unstructured data, there's many, many options for how you're managing that data and how you're governing it. From there, you're going to go through all the different examples on the right-hand side in terms of use cases. So to delve a little bit more into the data pipeline, again, the big picture is data in, insights out, and the steps of the AI ladder that you go through to achieve this. But from the data perspective, what you're doing is you're ingesting data, you're having to manage transient data, so you need a temporary landing zone. And depending on the type of applications that you're looking at, you may need to ingest at a real-time or streaming type of rate. So in this case, to get the data in, you're looking at temporary landing zones, capacity, storage requirements, and performance requirements, depending on your applications. Once you've got that data ingested, you're going to do typical ETL, extract, transform, and load of your data. This is in preparation for storing the data in the formats and paying attention to the requirements you need. And this is also the opportunity to leverage information that is associated with your data, which we call metadata. And so this is the type of information that can be very useful when it's tagged. And examples of that might be the creation date, size, geospatial information. So any kind of data that you can associate, any kind of information that you can associate to your data, you're going to want to need a system that helps you manage that metadata, and that'll facilitate faster searches into your data lakes. So all that data gets stored into data lakes or file systems or single namespace file systems. Hadoop is a typical example of that. And in this case, you'll need performance and capacity for that kind of information. Once you've got that data in a data lake, you're going to have some trained models based on data that you extract and learn from. And that information goes back and feeds back into the data that you're ingesting to determine what data you need, and it's an iterative process. So a little bit more on that specific step of developing the models, the AI models that you need. We talked a little bit about the data piece, and that involves the data preparation and setting it up in a model environment. You're going to likely want to have a data science workbench that helps automate and facilitate these steps, or you can do it from open source through Python and some of the other examples that are typically used with model development, like and using a framework like TensorFlow or PyTorch. So you've got your data, you're going to train, you have a runtime environment, and you will iteratively train, deploy, test, and until you get to a point where you've got a model that has learned from your existing data and you feel confident in the accuracy or whatever key metrics you're applying to those models to go out and inference. And that's the same as deploying your model and using typically APIs to call your model to come up with inferences or predictions of what your model is built to look for. The other factor here that's important is typically you need to be very confident in understanding what your model is doing, and explainability and fairness are two key features in enterprise AI that matter significantly in terms of being able to take an idea from a pilot or proof of concept to a secure and safe system that you can deploy into production. There's also a transfer in terms of skills and knowledge base and who's doing the work that goes from the data science team to the IT operations teams. And then of course you've got business developers that are pulling all this together to apply the model that you're deploying. So we talked a little bit about this use case exploration and the work that goes into the understanding your business use case, prepping the data, visualizing it, and determining a model, validating the accuracy and deploying it. But when you talk about how this really works in an enterprise environment, what we've just described here is a very small piece of the big picture. So the machine learning and deep learning activity and model development in particular is a small piece of everything that goes on in a production environment. So you've got resource management, you've got infrastructure, you've got monitoring, you've got analysis, like you just saw from Samir earlier on, you know, what is your system doing, what is your infrastructure doing, and what are your applications doing. You've got additional work that looks at feature extraction, in particular for machine learning. And across all of this, there are factors relative to security, privacy, and governance that need to be factored in to move into a production environment. We talked a little bit about this. These are the pillars of trust to get to production, and that is to ask the questions on whether your modeling, your AI infusion is fair. Is it easy to understand? Can you explain it? Is it secure? Are you exposed to slight changes to your model that could result in large changes to the insights and be attacked from a cyber attack perspective? These are the kinds of things that that need to be factored in. And is it accountable? Is it transparent? Is there bias in your data and your insights? So there's many tools that many areas of research, I should say, that are looking into this set of trust advantages, and we're starting to see a development of tools that that help manage these pieces of the AI lifecycle. So we'll make the comment here that once you've got your models built, your deployment plans in place, and you've built in trust to go to production, you now need to figure out how to deploy and where to host and where to build these this infrastructure. And a traditional infrastructure is typically not well suited for AI. One of the primary reasons for that is because of the amount of data that's involved and the types of microservices that are involved in building up these applications. So the key to look for are making sure that your data pipeline is not creating bottlenecks, that your systems are scaling to meet the demand, whether that's in a hybrid cloud environment or a capacity on demand type of environment, so that you're scaling to the needs of your business needs. And then making sure that you're optimizing to the actual work that that needs to happen, whether it's CPU and GPU for training engines or inference engines. So reiterating a little bit more on this, and to talk about where scale comes in, you need high performance and massively scalable storage capabilities. Ideally, you have tiered environments that allow for archiving at a lower cost, and so that your most your fastest storage is easily available to your to the applications that need that high performance the most, and making sure that it's secure. You need to be able to get access to your data and find your data easily. That's the idea of the meta tagging, as I mentioned earlier, or having a single namespace like a GPFS or spectrum scale in IBM terms of access to your data. It needs to be robust, and productivity here matters a great deal. The faster your data scientists access their data and are confident in their data, the quicker they can move to the analysis and evaluation phase of their models, where the real insights come through. And then finally, you need low latency and a broad access to capabilities to deploy out on the edge, whether that's automated APIs, microservices, built-in dashboard tools that help you build up your insights dashboards quickly. There's a lot going on the inference side and putting these models into your applications. So in terms of demands, there's a difference between whether you're training models or deploying them. The training side needs advanced I/O capability with bandwidth and low latency, able to manage large volumes of data, powerful accelerators with coherence to do the actual training computations, and scalability so that you can go across servers into clusters if you need. On the inference side, you need more flexibility in terms of range of storage. You need quick I/O, and you need to be able to deploy to the edge with the right tools and the right information, and able to handle real-time data. And typical inferencing happens either in the data center or in the cloud, so on servers. You can do on-prem or in-cloud inferencing. You can have multi-tenancy, meaning different groups, different applications using the same inference resources. And you can do on-prem or standalone, where you in fact are doing inference on the edge, where you get an image, for example, from a fixed camera on an assembly line, and get insight immediately right to the point of the edge where you're getting the information. Accuracy is critical, and again, I won't go through the whole list of items that factor into making sure that you've got a good inferencing system. So let's go through a couple examples that we've done in our environment. This is a typical example of all the pieces that come into a enterprise configuration for AI. We've got transactions that are coming in and IoT sensor data that's coming in. We have that information that's going into operational databases and warehouses, and we're doing analytics on that front right at the source of the data. We also have, to complement these operational databases and traditional databases, the more modern unstructured data databases, as well as Hadoop data lakes and file systems and object store. Across all of this, we've established systems for data governance, and from there you can establish a data science workbench that has all the open source tools and frameworks that are most popular. And you can see examples here like TensorFlow, PyTorch, Jupyter Notebooks, Pandas, data systems, and you have a AI grid that manages that work that's coming from the data science workbench. So where the training is and where the validation of the models, whether that be on a hybrid cloud or on premise. You can think of it as an AI grid of resources to manage the work that's coming out of the data science workbench, the workflow. And then from a deployment perspective, you can then move it to a service and have additional co-location for AI and making sure that your emerging platform is supporting the additional work that and insights that's coming from the AI inference piece. So more specifically, we have a manufacturing example looking for defects through an assembly line. And we started with a single factory with a local server and some local storage. We had devices that were fixed mount cameras and some sensors. And we built models using the cloud and an enterprise server to develop a model to recognize defects at various points in the assembly line. We then had replicated that across multiple factories, across multiple devices and checkpoints through the assembly. And at that point, needed a dashboard that provided information across multiple factories, across multiple inspection points, and was able to share the models that were being developed to the different locations and making sure they were rolled out consistently. So you can see how we went from a proof of concept just on one camera to make sure that it could recognize a defect, to a system of multiple defect recognitions across multiple assembly lines, across multiple factories, that now needed a system to manage all the models, all the data that was coming through all the factories, and making sure that the life cycle of the models being pushed out and then brought back in for new insights were being handled. So these required a more sophisticated infrastructure, where we went from just a single server to test things out in a device to a hybrid cloud environment with virtualization driven by containers and cloud packs to manage all that information and build up applications like overall dashboards that you could drill down into that managed the entire quality system to look for a specific defect. Another example that we've used recently relative to packaged goods, and this was in the pharmaceutical industry, to make sure that there was quality checks, inspection quality checks as the supply chain went through. So in terms of packaged goods, you have a manufacturer, you have an inventory of manufactured goods, and then you have a distribution and retailers with those goods. And throughout the entire supply chain, you could have inspection points. So we would have quality checks on the assembly line, similar to the previous example that I showed, inventory management, package check, individual package check and defect detection there. And then you could do inventory check at the retailer or at the distribution center. And a lot of these use cases are the visual use cases, where we tie these quality checks into starting with an image or a video, managing what you're seeing through trained models that have learned from those early or initial images, and then coming up with insights as new days go by or new information comes in. And that happens repeatedly through the life cycle of the supply chain. And in fact, one of the things that it does when you're doing these visual inspections, one of the applications to take that insight is to put it back into an asset management tool, where these are production systems that and processes that are already in place. And so the AI is giving you additional, more automated, less manual checks and balances as you go through your end-to-end process. So in summary, with the enterprise and applying AI to the enterprise, the best practice that we can advise is to think in terms of solutions, think in terms of workflows and end-to-end. So to get the most out of your AI and machine learning, deep learning models, you want to focus on the business problem and the use case. So are you able to articulate the use case and the problem you're trying to solve? Then to validate that you've got the right data to solve the problem, and making sure that your governance, your data governance and accessibility and ETL, everything that you do with your data is set up. We talked about how the actual modeling piece is just a piece of the overall workflow, and you've got data scientists in a workbench there applying this, but then that information to get into production needs to be pervasive across all the processes of your enterprise. You need to establish trust in every step and trusted partnerships throughout, so that the AI is explainable, not biased, and is trusted and secure. Infrastructure does matter when you deploy in production relative to starting just on a small use case, and how to get to scale makes a big difference in having access to the right resources at the right time, and being able to provision and manage your resource utilizations and all that makes a big difference in terms of success. And then finally, collaboration is pervasive on all of these, especially when it comes to open source tools and collaboration, and OpenPOWER in particular has a very important role to play in this open world that we're in, where collaboration for AI in the enterprise does make a big difference to business results. So I think that's it. Are there any questions in the chat?
Clarisse, thank you for the wonderful presentation about AI at scale in enterprise. And definitely, this is going to be very useful for, the students as well as the researchers who have been, participating in this webinar. And students, participants, any questions for Clarisse? There is a question from Dr. Gopal in the chat window, Clarisse.
Ah, okay. So maybe I should ask Dr. Gopal what he's asking about, or if it's.
Thank you. Is the mathematical formula you were mentioning in one of the use cases a symbol? The entire formula is a symbol?
Yeah, so what I mean by mathematical formula is machine learning and deep learning are based on mathematics. They're not based on rules or business rules. So the insight that you develop with machine learning and deep learning is by applying usually linear algebra type mathematics to your data. So by that I mean, for example, deep learning uses neural networks, and it transforms pixels into weights and biases, and then applies formulas, so dot products basically, to mathematically come up with features, low level, medium level, and high level features to determine what's important in the image from a deep learning perspective. So all I mean by that is that you're basically transforming your data into numbers and then applying algorithms to come out with the predictions on the back end of your models.
Thank you. You know, there's plenty of interest in the area of data analytics. We have a very good group in the department that works, plenty of projects. We have an ME with big data analytics as a stream, a postgraduate course. So we look forward to more such interactions.
Yes. So data analytics has been around for many years, and the real emerging piece of this and the very interesting piece is how you can apply machine learning and deep learning to some of the more traditional data analytics functions. And that's where I think your students will get a lot of interest in their work if they can embed some of the AI into the data analytics research that's going on.
Yeah, in this context, I wish to also mention that the webinar or this workshop circular was widely circulated, and I welcome all the participants who joined. Some of them are from other states, maybe. It has got a very wide circulation. Thank you so much. It has been in circulation.
Yeah, thank you, sir. Clarisse, there are two more questions in the Q&A window. One of them is actually how AI you used in biotechnology field.
How is AI infused in the biotech field?
Yes.
Okay, great questions. So there's a couple areas. One is traditional simulation relative to like genetics and things like that. You can apply AI to find a faster path to your end result. By that I mean, instead of doing simulations either randomly or brute force or through a specific set of parameter changes, you can apply Bayesian optimization looking at previous parameters and previous results to guess or predict what the next best simulation would be. So this is something called Bayesian optimization. We're working on that, and there's some great success stories of instead of 100,000 simulations, you're reducing it by an order of magnitude or more to get to your end result. So that's one area. Another area is with visual models, with diagnostics in particular, where you can build models that improve the diagnostic outcomes and predictions of tumor detection, melanoma detection, blood cell types. So a lot of visual models where you can either segment tumors or classify blood types. We did a recent COVID-19 example of different types of pneumonia from lung x-rays using AI. So that's a very popular set of applications. Another is with cryo-electronic microscopes, where it takes a long time to look at the outcomes manually, and those generate, typically cryo-EM will generate 5 petabytes of data a day of information. So having automation for cryo-EM analysis is a huge use case. And very popular because it gives you so much faster time to results again. There's also examples of data fusion, and that's, I think I mentioned this a little bit earlier, looking at research papers and looking for keywords and key information and extracting that through an appliance that looks at all sorts of data sources and basically answers questions to the point, looking at all those data sources in an automatic way. that's a data fusion AI application. And trying to think of what else. There's clearly safety examples in healthcare, as well as quality inspection in healthcare. But I would say those are the two primary ones: as improving your simulation time to results, and all the visual models that you can apply in diagnostics are the two most popular.
Very good explanation, Clarisse. Thanks for for that too. And there are two more questions. You can take a look at the Q&A window, and it's
Okay, sorry, I was looking at the chat questions. So
yeah,
yes,
yeah,
the
looks
Q&A.
like yeah.
Okay, textile design. Yes, in fact, we used a visual model to look at pattern flaws, which is quite an interesting use case of looking at pattern flaws in textile and anomalies. So anomaly detection with visual models is probably a good example in the textile business. And
the other question is, does AI help in marketing and programming field?
yes, so marketing and programming is a very popular example. And in fact, you're probably exposed to it, maybe not even with knowing. So for example, looking at customer churn, meaning when is a client likely to switch to a competitor? That's the type of data that they look at. And then they'll build marketing programs relative to that, or even individualized marketing promotions, so that they can identify who's likely to move to a different providers, like a telco provider or something, and provide maybe an incentive to stay with the current company. Many use cases relative to personalized information and targeting marketing campaigns relative to that, or email campaigns, things like that.
Sure. Yeah, there are two more questions in the same Q&A. Can you take a look?
Yeah, I see a stock, keeping inventory in stock, and absolutely. In fact, some of the challenges, of course, relative to visual models is privacy, but there are some cases of where they're actually trying to install cameras in supermarkets, for example, where you can visually see where the stock level is for different items, and real time or near real time get updates on when to restock. So that's one physical store example. But the idea relative to online stores is the same thing, is can you use AI to predict when you're going to be out of stock? And sometimes that's tied to weather data. So a local Walmart may need to overstock the number of umbrellas that they have if they know a hurricane is coming through. Or so there's a lot of insights that you can get relative to that. And relative to the online market, recommendation engines are also a very popular use case, where you can look, for example, at a set of sweaters that are in a certain tone and color, and pop up recommendations of shoes and bags that that might match. So probably more interesting for the fashionistas than the general public, but there's definitely some interest and some tie-ins relative to recommendation engines. And at Amazon, for example, you see this already. If you order something with that needs a certain type of battery, a recommendation might pop up with people buy this and this together, so that you don't order something and then realize that you didn't order the batteries that go with it. Okay, so do association, rule mining, and expert systems relevant to the current AI? Yes, and that's when we talk about rules-based systems, that's where we start. And there are a lot of expert systems now that are embedding AI in addition to their rules-based systems. And you'll see that with chatbots, for example, developing more and more insights with, for example, what's it called? Sentiment analysis. So you've got a set of rules-based expert systems, but you might be looking at responses real time and evaluating sentiment analysis, and then switching your actions based on those AI, embedded AI systems. All right, I think I've covered, oh, food chain and food scarcity. So one of the best blockchain use cases is food chain and food scarcity and food safety. And across every step of that, there's opportunities for AI in terms of visual models and analysis. So yes, definitely AI use case there. AI in the teaching field. So we actually had a project in the dentist, in a dental school, where we applied a model as a way to visually correct the angle of the instruments relative to the mouth and the student's hands. So it was a training technique, and we're starting to see this relative to virtual reality and our AR, where you go one step beyond some of the AI that I've talked about, which is more data and data center centric, where you're starting to see 3D training tools for teaching, for example, how to monitor and how to replace parts from technicians, for example. So there's definitely a lot of development in that field. And in terms of students, you certainly can apply, for example, maybe facial expressions or student activities and safety in your classroom. There's a lot of AI applications there. Okay.
Okay, I think you covered most of the questions, and for the if team participant, if you have any further question, please feel free to send us a note. You have the ADG group mail ID. How you registered, the same way you can send an email also. We'll be there to answer the questions too. And also, as I said before, if you come out with a good project idea, or if you want to do some projects, definitely you can send us a proposal. We will look into that, and we will also provide you some guidance as well as the infrastructure for executing the projects too. With this, I'd like to thank the panelists, the speakers especially, and also the participants who have been staying for the last 2 hours nearly for this the two sessions, and also I'd like to thank the Dr. Gopal from Anna University, who has given this great opportunity to present about our technologies to the students in Anna University as well as across India and other part of the world too. With this, I'd like to conclude this session, and looking forward to meet you all in the next workshop. Thanks again. Dr. Gopal, you want to add a few words before we close this webinar?
Again, on behalf of my head of the department and my colleagues who have department, I wish to thank both Dr. Samir Shende and Clarisse Hedglin. As a matter of fact, Mr. Ganeshan and Sami has been one of our old students. Happy to see him. And for the record's sake, we are really looking at the 150 participants now after 2 hours. It was close to 200 when we started. So it has been a wonderful seminar, and we thank both the speakers for answering all the questions with plenty of clarity, a lot of easy way of appreciating what exactly has been taught as a lecture. We hope that the online collaborative environments will catch on further, and who are, as I said, the southern tip of Tamil Nadu, Nagarkoil, will be happy to participate in these events and make best use of it. Thank you. Technology is like that. We also need to ensure that those who teach technology are also in the loop at the earliest. Thank you.
Very much for organizing.
I'm off on the video to ensure that we don't have too much of bandwidth constraints.
Yeah, thank you, sir, and thanks to everyone. And I'm closing the webinar now. Thank you.
Thank you so much.
Bye-bye.